we are going to be looking at statically indeterminate structures. And then to work with statically indeterminate structures, there are several methods that are usually used, amongst which we have the first method, which is called Lifa, that's in Chinese. So first we look at the steps that we take in calculation. Say they require us to draw a bending moment diagram of a structure that is statically indeterminate. What are the methods that we take in calculation? The first one is that we extract out a basic structure by forming an equivalent statically determinate structure from the statically indeterminate structure. Here what we mean is that if I do have such a structure like this one here, we know that at this point it has got how many supports? It has got 3 reactions. That is a force in the vertical, a force in the horizontal, and then it has got a moment, isn't it? Then here it has got an extra vertical reaction, isn't it? So we know that a rigid body like this one here requires only 3 supports to be able to be statically determinate. So in this condition that it has got an extra support at this point here, how do we get to convert it into a structure that is statically determinate but then still equivalent to this very structure that has been given? So what we can do that by removing this support here and replacing it with a force. So that means that our system would be converted into a system of this nature here, like that. Then what I do to keep my structure equivalent to what I had initially, I add a force at this point, and then this is a force that we usually name x1, which we usually give a magnitude of 1. So that is one of the ways in which we can do that. Alternatively, another person can do it by releasing the moment at this point, and then the structure is converted into a simply supported beam of this nature. Then here we've got this hinge support, and then we've removed off the moment, isn't it? So what we do, we add on a what? We add on a unit moment. That now would be our xe. Our x1 is equal to a 1. So this structure is similar to this one. So from this, what we see is that in the first step of converting a statically indeterminate structure into a basic structure, there are different models that one can come up with depending on their preference. That is the first step. Then the next step that we do is that we add a unit force at a point whose displacement is required. That is, if in case they require us to find a displacement, but usually we can just keep it up by using the x1 at a point whose reaction has been taken off. Then we just replace it by x1 is equal to 1. Then after that, we draw the what? We draw the bending moment diagram due to the action of the unit force and the action of the original force on the structure. Then after doing that, come and solve for x1. In the equation, delta 11 x1 plus delta 1p is equal to 0. That one we shall get to know what this delta 11 and x1 and then the delta 1p represents when you look at the example. Then after that is done, we compute the moment on the structure from m1 x1 and then the plus mp is equal to 0. This m1 here would be the moment that is on the moment diagram due to the action of the unit force, that is x1 is equal to 1, and then the mp is the moment on the diagram with the original loading, then equal to m. And then having done that, we come and draw the bending moment diagram. So let's look at this by means of an example. Assuming that we have this as our first example, and they require us to draw the bending moment diagram. What do? If we are to use the first method, we say that the first thing is that we need to come up with a basic structure. And for that case, our basic structure, we know that this one is to 1 degree indeterminacy, since this one has got 3 reactions, and at this point we've got 1. So assuming that I relax this side and then I come up with my basic structure as this one, like I have 3 reactions, isn't it? Okay, then I have the original loading on the structure, then the only difference is now on the hinge. So what I do, for the sake of that part where I have the hinge, I can add there the unit force, that is x1 is equal to 1. So this is what I would be calling as my basic structure, BS. After I come up with my BS, we say that the next step is that I come and I draw the what? I come and I draw the bending moment diagram due to the action of the original loading, that is of magnitude Q, and then also draw the bending moment diagram due to the action of the force x1. If say I draw the bending moment diagram due to the original loading, this system here is a system that has got the action of distributed load. So under the action of distributed load, my bending moment diagram would be like this, since it is a cantilever beam. And then at this peak point, I would be having my value as a half QL squared. Then I come and I draw the bending moment diagram due to the action of the unit force x1. x1 is equal to 1. So this one here pushes it upwards, then our tension region is down. So we draw our bending moment diagram on the lower end, since it's the part that is under tension. So that one there would be forming a triangle, a triangular shape like that, of magnitude force times distance, that would be L. Having drawn our bending moment diagrams, this is M, M1. Now the next part, we say that we have to come and solve the equation that was given by delta 11 x1 plus delta 1p is equal to 0. So that means that we need to first find the delta 11 and then the delta 1p. Sorry, this sigma. So sigma 11 is given by the equation integral of, that is m1 times m1, then divide by ei ds, like that. So now this equation, if at all you recall, it's similar to the equation that is used to calculate the displacements in the previous section of statically determinant structures. So in this case here, we are simply multiplying the action of the unit force moment diagram by itself. So this sigma 11 would be equal to, now since we only have one shape, which is a triangle here, and then the triangle is part of the basic diagrams that we talked about, isn't it? So what we need is its area. So 1 over EI would be a constant, then into its area is given by a half B. Our B is equal to L, the length of the triangle, then times its height, which is also given by L, this L here. And then times, now since we are multiplying it by itself, that means that we need to come and find where the center of it is. So if you recall, we said that from this point up to this point, it takes on a length of 2/3 of L. So therefore, I find my sigma 11 as being equal to 1 over 3 EI L cubed. Then after doing that, the next I come and I find my delta 1p. So delta 1p would be equivalent to integral of m1 mp divided by ei times ds. Actually, yeah, this one is exactly the same as that of the diagram multiplication method. So we shall use the same idea, whereby we say that we get our area from the MP diagram, then we find our position of the center from the M1. So the delta 1p would be equal to, open the brackets, we only have one shape, and then that is that curved line that is also part of our basic structures. So our area would be given by the area of that shape, we said is given by a third BH. Our B is equal to L, that is from here to here, times L, then times its height, a half QL squared, then times the position of the center. So if you actually recall, we said that for this shape here, like the length from this base up to this part is given by 1 over 4 times the length, a quarter of the length. So meaning that from the tip up to this point here, it would be what? It would be, let me write it here, it would be 3 over 4 L. like that, since the other side is a quarter. So therefore, this height here is now what shall be calling our y, or the height at the position where the center is. So we also observe that our triangle has got a height of L, and then the base is also L. Therefore, the ratio of the height to the base is 1 to 1. Therefore, for this triangle here also, the ratio of its base to the height would also be 1 to 1. Therefore, our height y would be equal to 3 over 4 L. Then we have to take note of the signs. Now, when we look at these two shapes here, we see that this shape, the tension side is up, while on this diagram, the tension side is up, while on this one here, the tension side is down. Therefore, we need to have a negative sign here. So we come and let's see what we get. This one cancels with this. Then we shall be having our answer being equivalent to 1 over 8 e I ql power 4 with a negative at this point here. So having calculated the sigma 1 and then the delta 1p, the next is to what? The next is that we are supposed to find the value of x1. x1 is calculated from the equation delta 11 x1 plus delta 1p is supposed to be equal to a 0. So therefore my delta 11, we say that was L cubed over 3ei. This is supposed to be equal to, this was a negative, so this when you cross the equation it becomes a positive. So positive 1 over 8 e I q L cubed. So this is times x1. Therefore the ei and this ei cancels, this is L power 4. This one cancels, then here we are left with only an L. Therefore our x1 would be equivalent to 3 over 8 QL, like that. So having done that, the next part is now to come and work out the equation m1 x1 plus mp. So it's supposed to be equal to m, the final moment. So here what we do is simply now just have to come and superpose the two bending moment diagrams. So for the sake of the MP, we already have the value, but anyway, let me magnify it from here. For MP, let's say this is a structure for MP, and then for the sake of the M1, we have a structure like this. Then here we had this like that with our peak value as half Q L squared. While for this one here, our structure was a triangle of that nature. Then we say that the value of the final moment of this point would be equivalent to m1 times x1. So here m1 times x1, our x1 is 3 over 8 QL. Then our value at that peak, the value of x1 is L. So the value of m1 is L. So when I multiply the two, I would be having 3 over 8 QL squared, like that. So now to draw my bending moment diagram, I now have to come and add up the values of the moments at corresponding points, and then I derive the format of the curve. So for the sake of this one, since it's a curve, I need 3 points to draw it. I need to find the moment, the combined moment at this point, then at this point and this one, then let's say also the moment that they share at the center. So what we do is just by simply adding up the moments at the corresponding places. So now my final bending moment diagram would be like this. So I know that if I'm to begin with this end here where I have the rigid support, I have to add the half QL squared. Then now this one plus negative 3 over 8 QL squared is negative because they are on different sides, and then the one which usually is on the lower side, just as on a number line, takes on a negative. So when I get a half QL squared minus 3 over 8 QL squared, I get 5 over 8. So 5 over 8, I get a positive. That means it still keeps on the upper side. So we shall be having our value here as 5 over 8 QL squared. Then when I add up the moments at this point and then at this point, I know it remains a 0. 0 plus 0 remains a 0. Then now I come and I get my third point as, let's say, the center here. So at the center here, I know that my moment, like the general equation for the moment at any point on a cantilever beam due to a distributed load is given by a half Q L squared, yeah, and then now at the middle point our L is equal to L over 2. So therefore here I would be having my moment as 1 over 8 Q L squared, that is at this point here. Then for the sake of the triangle, we also need to come and find the moment at a length L is equal to L over 2. So at the point L is equal to L over 2, we need to come and find the value of the moment here. So we know that the big triangle, this one here, has got a ratio of height to base as 1 to 1. Therefore, that means that the ratio of this height to this base here must also be similar to that. So that means that that if, let's say, the base here becomes a half, that means the height must also reduce by a half. Therefore, this one here becomes 3 over 16 Q L squared. If you don't understand it this way, you can use the idea of similar triangles and then you compute out the value of this height here. So that means that now when I come and I add this 1 over 8 minus 3 over 16 QL squared, I come up with my value as negative QL squared over 16. That means it's to be found down somewhere there, somewhere here. So knowing the 3 points, I can go on and draw my bending moment diagram. So the final bending moment diagram would be with this point having a value of Q L squared divided by 16. Then here we said it was 5 over 8 Q L squared. Then here we have a 0. Yeah, so that's how we use the fourth method to draw the bending moment diagram. Let's look at the next example. The structure is as shown above, and then we are required to draw the bending moment diagram. So we are going to be following the same steps. We say that the first thing that we need to do is to come up with a basic structure. So with the basic structure, we still see that